In this tutorial, we will use transient simulation to investigate the large signal response of the operational amplifiers. We will use the basic non-inverting amplifier circuit from the previous tutorial. We'll use R2 equals 18K and R1 equals 2 kilo ohms, so our overall gain will be 1 plus 9 equals 10 volts per volt. Since we're interested in the large signal response, we will adjust our input voltages so that the expected output voltages would ideally go past the supply voltages. Our supply voltages are plus or minus 15 volts. For our transient characteristics, let's choose an offset voltage of 0 volts for the time being, an amplitude VA of, let's say, 2 volts, and let's keep our frequency at 1 kilohertz so that we are well below the 3 dB bandwidth of this amplifier, which should be on the order of 400 kilohertz. So we have a sinusoidal signal source with an offset voltage of 0 volts, an amplitude, peak amplitude of 2 volts, and a frequency of 1 kilohertz. We'll do a transient analysis. We'll simulate this for, let's say, 10 periods. 1 kilohertz equals a period of 1 millisecond, so I'll choose 10 milliseconds. And why don't we go with 10 microseconds for our maximum time step. We are only interested in the output voltage. I can click delete. I will choose X range auto always and Y range auto always. So if you look at the vertical and horizontal lines on the left next to the check mark, these determine if the x-axis is going to be a log scale or a linear scale. Since we're plotting a transient response, that is a response versus time, it's probably best to keep these as linear figures. Alright, let's now run this simulation. As you can see, the output signal is not quite sinusoidal, and in fact the output is clipping. We actually observe several effects here. The first one is the output clipping. If I switch to cursor mode to check the peak value, and the peak value is 14.1 volts and the valley is minus 14.1 volts in this case. These are well below our expected gains, right? 2 volts times 10 volts per volt should have given us 20 volts, but because of the supply voltage limits, we do not quite make it that far. Further, since the LF351 is not a rail-to-rail amplifier, the output voltage actually saturates or is limited to something below the supply voltages. The output doesn't even make plus and minus 15 volts. Another thing that may not be quite obvious is that the output here is kind of linear instead of sinusoidal. If we were to change the signal input to, say, 0.2 volts and rerun this transient simulation, we'd see something that looks more sinusoidal. If we were to make this input even smaller, say 20 millivolts, that looks even nicer. Now notice that another effect is now manifesting itself in the simulation. The LF351's offset voltage is now coming into play, shifting the output voltage by several millivolts. Let's bring this back to 2 volts. And in the transient, let's just look at 3 periods. You'll note that here, switching from the peak and going downwards and the downwards edge, this is very much linear. It doesn't look sinusoidal at all because the response is now limited by the slew rate. The small signal response is limited by the frequency response of the amplifier. The large signal response is limited by the slew rate. They come from 2 different parts of the LF351 operational amplifier circuit. The slew rate is determined by the output circuitry, the output stage, whereas the 3 dB frequency and the small signal frequency response is determined by the frequency compensation capacitor CC, which is, according to the schematic, a 10 picofarad capacitor. We'll study these more in 343 when we talk about frequency response and stability of operational amplifiers, as well as output stage design. So when you're dealing with operational amplifiers, if you have a small signal swing at the output, your frequency response is determined by the small signal response of the amplifier, and you should be looking at an open loop frequency response, such as the what you plot here or here. But if you're dealing with a large signal output, your response is going to be determined by the slew rate limit of the amplifier. Furthermore, let's investigate another aspect of the simulation. We will use a Furrier Transform to obtain the frequency characteristics of this signal. We can change the scale of this circuit, deselect auto scale, and look, for example, at changing the x-axis. And in the frequency response, we see many peaks. We were investigating a 1 kilohertz signal, yet we see peaks, responses at 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on. We can make that response a little bit better by making this output signal less distorted. So if I were to look at a 2-volt output signal, and I run the transient analysis again, I should see something much better. The problem that we run into now is that we are dealing with only 3 periods. In the SP, you'll see that the more periods that you have, the nicer this Furrier transform is going to look like. I'll make that steps a little bit coarser, but increase the time range. You'll notice that making the steps coarser and transient made that signal look a little uglier. So we'll bring it back to 10 microseconds. And now we have a much cleaner looking Fourier transform, a frequency response, where there's a peak at 1 kilohertz only.